Welcome everybody once again. So we are in our fourth module. We are studying about the Kanis method. So today in Kanis method we are going to analyze a 3-span continuous beam with overhang. So this is our given problem. We have a 3-span continuous beam. Our 3-span continuous beam is beam ABCD. So AB is one span, BC is another span and CD is our third span. AB is of span length 6 meter, BC is of span length 5 meter and CD is of span length 5 meter. Now we have a 2 kilonewton per meter uniformly distributed load in the span AB. There is a 5 kilonewton load acting at a distance of 3 meter from B in the span BC. And there is an 8 kilonewton load acting at a distance of 2.5 meter from C in the span CD. This 8 kilonewton is acting at the mid span in the span CD. And the moment of inertia are for the span AB, moment of inertia is I. For BC, the moment of inertia is 2I. And for CD, the moment of inertia is I. So this problem is different from the previous problems in the way that the support D. See, at D, you do not have any support. At the right end, it is an overhang. So CD is an overhang. So CD behaves like a cantilever. CD is an overhang. So in a few steps, you should be very careful how to calculate the moments. We will move on to our solution. So step 1. So as usual, our step 1 is to find the fixed end moments. So we will determine the fixed end moments. So when we are considering the span AB, we have fixed end moment MFAB. So MFAB will be equal to minus WL square by 12 and MFBA will be equal to plus WL square by 12. I have explained it to you earlier. So fixed end moment means we have to assume the support as fixed supports. Either it is hinged or simple supports or a roller support or a fixed support. You have to assume the support as fixed support. And when you take this section, we know when you are taking the bending moment about a section, the left anti-clockwise becomes negative and the right clockwise becomes negative. That is why when you are taking M of AB becomes anti-clockwise. So it is represented as minus and right clockwise is represented as positive. So since it is UDL, the formula is minus WL square by 12 and at the right end it is plus WL square by 12. Now, if it is a concentrated load, we will assume both ends are fixed. Therefore, the formula for determining the fixed end moments will be equal to, at the left and right it is negative anti-clockwise and clockwise it will be positive, and the formula will be equal to minus WAB square by L square, and here it will be plus WA square B by L square. Okay. So MFBC will be equal to minus WAB square by L square. MFCB will be equal to plus WA square B by L square. Now for the span CD, D do not have any support. So it is an overhang, right? So when it is an overhang, only there is a support at the joint C, and we have an 8 kilonewton load acting at a distance of 2.5 meter from C. Therefore, our bending moment, fixed end moment at C will be equal to M of CD will be equal to this 8 into 2.5. 8 into 2.5 kilonewton. So since it is the left of the support, that will be minus. So minus 8 into 2.5 kilonewton. There will not be any moment at D because there is no support at D. Okay. So since this is an overhang, MFCD, that is fixed end moment at C when the far end is D, will be equal to minus 8 into 2.5. Okay, so we will substitute the values. So for M of AB, it is minus, W is given as 2. So it is 2 into L is 6, 6 square divided by 12. We get the value as minus 6 kilonewton meter. So similarly for MFBA will be equal to plus 2 into 6 square divided by 12. We get the value as plus 6 kilonewton meter. Now for the span BC, it is minus, W is 5 kilonewton. So 5 into A is 3 meter and B is 2 meter. So 3 into 2 square divided by L square. See, this distance is 2 meter. So that will be equal to minus 2.40 kilonewton meter. So M of CB will be equal to plus 5 into 3 square. A is 3. So 3 square into B is 2 divided by L square. L is 5 here, right? So 5 square, here also it is 5 square. We get plus 3.6 kilonewton meter. Now MFCD will be equal to, since it is an overhang, it is 8 into 2.5. So it is minus 20 kilonewton meter. Now we will move on to our second step. Our second step is to determine the rotational factors. So step 2, determination of rotational factors. We know the formula, rotational factor will be equal to minus half of the distribution factor. So for finding the distribution factor, we will consider the intermediate joints. So here we have two intermediate joints, that is joint B and joint C. Okay, we have two intermediate joints, joint B and joint C. And remember, when you are considering the joint B, BA, the far end is fixed. For BC, it is the extreme support. C is the extreme support. Okay, we have to consider the joint D also, right? So C is also an intermediate support. So this support C also will be considered as fixed support. When you are considering joint C, B is an intermediate support, so that will be considered as a fixed support. So when we are finding the relative stiffness, we know if the far end is fixed, the relative stiffness is I by L. And if the far end is hinged, the relative stiffness is equal to 3 by 4 I by L. So here everywhere it is I by L. Now we will consider the joints. We have the joints. We have two joints B and C. And the members joining the joint B is BA and BC. and the members joining the joint C are CB and CD. So now we will find the relative stiffness. We know relative stiffness is represented as a small k. So it is I by L. So for the span BA, I is I and L is 6 meter. For the span BC, again it is I by L because the far end is assumed to be fixed. So I is, for the span BC, I is 2I and L is 5. Now for the span CB, B is the far end. The far end is assumed to be fixed end. So it is 2I by 5. For this, because for the span CB, I is given as 2I in the question. Now for CD, the end D, we do not have any support. So you can take it as 0. Now we will consider the sum. So sum, that is sigma k, I by 6 plus 2I by 5, we get 17I by 30. Now here it is 2I by 5. So now we know the distribution factor is equal to k by sigma k. So I by 6 divided by 17 I by 30, we get 5 by 17. 2I by 5 divided by 17 I by 30, we get 12 by 17. Now you add these both, that is 5 by 17 plus 12 by 17, you should get, the summation should be equal to 1. Now, here it is 2I by 5 divided by 2I by 5, the distribution factor is 1. For CD, it is 0. In moment distribution method, we don't consider this CD. But here we have to consider this joint C also. The reason is in order to find the rotational factor. There the distribution factor, that is not necessary, right? And even if you find, there is no mistake in it. Now, the rotational factor will be equal to 0.5 times, minus 0.5 times, right? That is minus half, minus 0.5 times of distribution factor. So 5 by 17 multiplied by minus 0.5, we get minus 0.1471. Minus, 12 by 17 multiplied by minus 0.5, we get minus 0.3529. So you add these both, you should get minus 5. Minus 0.5. Add these both, we should get minus 0.5. Adding the distribution factor at the joint, we should get 1. Adding the rotational factor at the joint, we should get minus 0.5. So here it is 1 into minus 0.5, we get minus 0.5. Here it is 0. Okay. So that is all about the rotational factor. Now we will move on to our third step. Our step 3 is finding the resultant restrained moment. Step 3, we will find the resultant restrained moment. So we know how to determine the resultant restrained moment. We will find the resultant restrained moment for all intermediate joints. So we have the intermediate joint at B and intermediate joint at C. So MF B will be equal to restrained moment. Resultant restrained moment at B will be equal to. So at B we have MF BA plus MF BC. So fixed end moment at B. So summation of all the members, summation of the fixed end moment of all the members meeting at joint B. That is why it is MF BA plus MF BC. So that is equal to, we have found it in our first step, MF BA is equal to plus 6 and M of BC is equal to minus 2.4. So we get plus 3.6 kilonewton meter. Now M of C is equal to M of CB plus M of CD. M of CD will be equal to, okay, we have M of CD, right? So that is equal to plus 3.6 minus 20. So we get minus 16.4 kilonewton meter. Now we will go for the Kanis iteration cycle. That is our step 4. Okay. So step 4, we will go for Kanis iteration cycle. So we know for drawing the Kanis iteration cycle, we have two intermediate joints, that is B and C. Therefore, we have to draw two boxes, right? So two boxes for joint B, one small box and one big box for joint B, and one small box and one big box for joint C. So this is joint B, joint C. So you can have joint A here and D here. Okay, so from A to B, B to C, and from C to D. Now, we have to write the restrained moments inside the smaller box. So, at B, the restrained moment is plus 3.6. So, we can write plus 3.6 in the smaller box. At C, the restrained moment is minus 16.4. So, we can write minus 16.4 in the box corresponding to joint C. Now we will write the rotational factors. We know the rotational factors are, at joint B, the rotational factors are, for BA it is minus 0.1471 and for BC it is minus 0.3529. So for BA it is minus 0.1471. 1471. For BC, the rotational factor is minus 0.3529. 3529. For the joint C, the rotational factor for the member CB is minus 0.5. And for CD, the rotational factor is 0. Now we will write the fixed end moments. So the fixed end moments are for AB, M of AB is minus 6. M of BA, we have obtained in our first step. Fixed end moment M of BA is plus 6. M of BC is minus 2.4. M of CB is plus 3.6. M of CD is minus 20. M of DC is 0. We don't have any fixed end moment at D because it is an overhang. Now we will find what is small MAB. Small MAB means the rotational contributions, right? We will determine what is the rotational components, rotational contributions. So here it is. We will find MAB, MBA, MBC. We will draw the lines at B and C, at A and at D. We will go for some 5 or 7 iterations. So here it is m, small m a b, small m b a, small m b c, small m c b, small m c d, and small m d c. So we know the small m means, small m a b means that is nothing but the rotational contributions. Small m a b means the rotational contribution of end A to m a b, right? M a b means rotational contribution of end A to the final end moments AB, MAB. MBA means rotational contribution of end B for the moments MBA. So that is the meaning of that. So now we will go for iterations. So iteration 1, 2, 3, 4, 5, 6 and 7. The reason we are going for 7 iterations is in order to get the accurate results. If you go for more iterations, see more the number of iterations, we will get more accurate results. Okay. So this MAB means rotational contributions. So we will determine this rotational contributions in our next step, and we will write the values in this cycle. So step 5 I will write here. So step 5 we will calculate the rotational contributions. So we know the formula for rotational contributions, right? Already we have seen it in our last few problems. So first we will go for iteration 1. So if we open a tabular column, that will be easy for us. Okay. So shall we open a tabular column? Iterations. So first iteration. So we know the formula is, we need to find m, small m, right? Okay. Now, this MAB will be equal to 0 because this A is fixed end, right? A is fixed end. So there will be any rotational contribution from a fixed end. So MAB will be equal to 0. Now, MCD, that is this MCD also will be equal to 0 in our first iteration, and thereby the reason is MCD, this is a cantilever. See, since this is a cantilever, this is an overhang, CD is an overhang, so this behaves like a cantilever. So there will not be any rotational contributions from joint C to joint D, or there will not be any rotational contributions from joint C to joint D or to joint B. So it is 0. Reason is, this is the fixed end of a cantilever. See, even though this C is simple support, when it behaves as an overhang, it should be considered as a fixed support. This behaves like a cantilever. So if it is behaving like a cantilever, the support C should be considered as a fixed support. That is why while determining our distribution factors also, we have considered this C as a fixed support. The far end as fixed because it is an overhang. Now, to start with, we will assume this MCB is equal to 0. So you can find either MCB first or MBC first. See, in the first two problems, we assumed MBC is equal to 0 and the first step we determined MCB. So here for a change, see nothing wrong, you can calculate in that way also. Here for a change, we are assuming MBC equal to 0. See, in the previous problems, we assumed in the previous problems, we assumed MBC is equal to 0. We found MCB in our first iteration as the first step. Here for a change, let us assume MCB is equal to 0 and let us find MBC first, right? So in our first iteration, we have to find the value for MCB. MBC. Assuming MCB is equal to 0, we will find MBC. So we know the formula for MBC will be equal to the rotational contribution for BC multiplied by MFB plus MCB. Okay. Similarly, MBA. See, we have to find. See, here everywhere it will be 0. It will be 0 everywhere. Here also everywhere it will be 0. Now, only three components are there. MBC, MCB and MBA. So, we will find MBC, MBA and then we will find MCB. So, only three components, right? So, first is MBC. After finding MBC, we will find MBA. BA. MBA will be equal to, wait. Goes bigger size. And also here there is a mistake. It is capital DC, capital CD, capital CB. BA, BC, CB, CD and DC. Okay, first iteration we will find MBC. So MBC will be equal to RBC multiplied by MFB plus MCB. Now MBA will be equal to RBA multiplied by MFB plus MCB. MCB will be equal to RCB multiplied by restraint moment at C. See, these both cases restraint moment at B. Here it is restraint moment at C plus the rotational contribution of the nearer support, that is MBC. Okay. So we will go for the iterations 1, 2, 3, 4, 5, 6 and 7. Okay. So the first iteration. For the first iteration, what is RBC? RBC is minus 0.3529 multiplied by MFB is 0.36 plus. So initially we will assume this MCB is equal to 0. So what we have is RBC, that is minus 0.3529 multiplied by MFB is plus 3.6. Initially we will assume MCB is equal to 0 because we have not obtained MCB is equal to 0. So we get minus 1.270. Now MBA is equal to RBA. RBA is minus 0.1471 multiplied by MFBA is 3.6 plus 0. We get minus 0.530. Now MCB is equal to RCB. RCB is minus 0.5 multiplied by MFC is minus 16.4 plus MBC. The small MBC we have already calculated it as 1.270. So 1.270 we get plus 8.835. Similarly, for the second iteration, MBC is equal to RBC. RBC is the same 0.3529. MFB is also not going to change. But MCB, we have determined MCB. MCB is 8.835. So it is plus 8.835. We get the value as minus 4.338. Now MBA is equal to RBA minus 0.1471 into 3.6. These are same. The only thing changing is MCB. So MCB is plus 8.835. We get the value as minus 1.829. Here RCB is not changing. So minus 0.5. MFC do not change, minus 16.4 plus MBC is changing. So last step MBC, the value is minus 4.338. So it is minus 4.338. So we get plus 10.369. Similarly, for the third iteration, minus 0.3529 into 3.6, only change will be MCB. So last found MCB is plus 10.369. So plus 10.369, we get the value as minus 4.930. Here it is minus 0.1. Minus 0.1471 into 3.6. This change MCB is plus 10.369. We get minus 2.055. Similarly, minus 0.5 into minus 16.4. This changes. MBC, what we have found at the last is minus 4.930. Minus 4.930. We get the value as plus 10.665. Similarly, for the fourth iteration, minus 0.3529 multiplied by 3.6. Now plus 10.665. We get minus 5.034. So similarly, you have to proceed this, okay? You have to find all the 7, for all the 7 iterations. You can stop with 5. If you want more accurate results, you can continue. So we get, I will give you the values now. You can proceed with the same procedure. So minus 5.034, next value is, see you can calculate, right? You please calculate. I will give you the values. Minus 2.098 plus 10.707 Now for cycle 5, the values are minus 5.049 minus 2.105 plus 10.724. For iteration 6, the values are minus 5.055 minus 2.107 plus 10.728. For the 7th cycle, the values are minus 5.056 minus 2.108 plus 10.728. Okay, so these are our final values. Now we will write all these values of all these iterations in our Kanis cycle. See, we can see the last iteration is very closer to the neighboring iteration. That is why we have stopped with the 7th iteration. Here there is more variations, 0.049, 0.055. So, okay, in order to reduce this difference, we have gone up to iteration 7. If you go for more iterations, we will get more closer results. Okay, now we will write all these values in our cycle. So, writing all these values in the cycle, we get the values for MBA are minus 0.530, minus 1.829, minus 2.055, minus 2.098, minus 2.105, minus 2.107 and minus 2.108. For MBC, the values are minus 1.270, minus 4.338, minus 4.930, minus 5.034, minus 5.049, minus 5.055 and minus 5.056. For MCB, the values are plus 8.835 plus 10.369 plus 10.665 plus 10.707 plus 10.724 plus 10.728 plus 10.728. So now the last values should be considered for MBA. This is MBA, MBC and MCB. So the last values, the values obtained for the last iterations should be considered for calculating the final end moments. So our steps, how many steps are over? 5 steps are over. So 6th step. So step 6, we will compute the final end moments. Step 6, computation of final end moments. Computation of final end moments. So computation of final end moments, we know, I have already explained you, this Kanis method is an extension of slope deflection equation. So we know the slope deflection equation is MAB will be equal to MFAB plus 2EI by L into 2 theta A plus theta B. So this is expressed as MAB plus 2MAB plus MBA. This is the rotational contribution. Okay. So we saw these things in our derivation. 2MAB plus MBA. So we have obtained what is M small m. Now in general we will write this as MFIJ plus 2MIJ plus MJI. Right, this is the general term. So this is our final end moments. So fixed end moment plus 2 times the rotational contribution of I to the end ij, and 1 time the rotational contribution of the end j for the end moment ji, for the end moment ij. Okay, so now we will write mij, sorry, mij. See, general term when we write it is mij is equal to m of ij plus 2mij plus mji. So, okay, this is. So, mij, we will write mij first, then we will write mfij. So, mfij, then we write 2mij, and finally we write mji. So, what is mij? Mij is the summation of. So, mij is equal to mfij plus 2mij plus mji. So, how many end moments we have? See, we know, we will look into our beam. We have the end moment at A, B. So, MAB, MBA, MBC, MCB and MCD. So, we will write here MIJ as MAB, MBA, MBC, MCB and MCD. So, MFIJ, that is fixed end moment at I and J. I is A, J is B here. Here I is B, J is A. Here I is B, J is C, I is C, J is B, etc. It goes on like that. So, in the first step, we have determined our fixed end moments as M of AB is equal to minus 6 kilonewton meter, M of BA is plus 6, M of BC is minus 2.4, M of CB is plus 3.6 and M of CD is minus 20.0. See, I forgot to write this. See, from this we have obtained actually this is our MBA, this is our MBC and this is our MCB. Now, two MIJ. Here I is A and J is B. So, 2MAB. 2MAB. So, 2MAB is 0. This is MAB. MAB is 0. So, write 0 here. Now, MJI means J is B, I is A. That means MBA. MBA is minus 2.108. So, add these three, minus 6, minus 2.108, we get minus 8.108 kilonewton meter. Similarly, the end moment at B when the far end is A. So, MBA is equal to plus 6. So, 2 times IJ. Here I is B, J is A. So, MBA, small MBA will be equal to minus 2.108. So, 2 times minus 2 into 108, we get minus 4.216. Now MJI means small m AB. Small m AB is 0. So adding these three plus 6 minus 4.216 we get plus 1.784 kilonewton meter. Now MBC is MFIJ you have written as minus 2.4. Now small mij, I is B, right? So 2 MBC. So 2 MBC is minus 5.056. 2 MBC means 2 times minus 5 into 2 into minus 5.056. We get minus 10.112. Now JI means CB. MCB is plus 10.728. So adding all these minus 2.4 plus minus 10.112 plus 10.728 we get minus 1.784 kilonewton meter. Now MCB, so MIJ, small ij means small MCB. Small MCB is plus 10.728 multiplied by 2 you get plus 21.456. JI means small m BC. So small m BC is minus 5.056. So adding all this you get plus 20.000. Add plus 3.6 plus 21.456 minus 5.056. Now MCD, it is MCD. MCD is, this is MCD, right? MCD is MBC, sorry. It is MCB. Here you have MCD. So that is MCD is 0. MDC is also 0. So MCD is 0. MDC is also 0. So you get minus 20.00 kilonewton meter. So this is our final end moments. See, this is our final end moments, which we will draw the bending for with the help of which we will draw the bending moment diagrams. So before drawing the bending moment diagrams, we need to find the simple beam moments. Okay, so that we will calculate in step 7. So step 7. Step 7, we will find the simple beam moments. So simple beam moments for the span AB, there is a 2 kilonewton per meter loading. Span length is 6. So for the span AB, the maximum moment will be, M max will be at the center, it will be a parabola. It will be a parabola and the value is WL square by 8. So it is 2 into 6 square divided by 8. We get 9 kilonewton meter. Now for the span BC, we have a 5 kilonewton load acting at a distance of 3 meter from B, totally 5 meter. And the formula is M max will be equal to WAB by L. So W is 5 A is 3 into 2 divided by L is 5. You get 6 kilonewton meter. Now for the span CD, it is an overhang, so there will not be any simple beam moment. Okay, now we will draw the beam moments. We will draw the bending moment diagram. So in order to draw the bending moment diagram, first of all we will draw the simple beam moment diagram. So our simple beam moment diagram is for the span AB. We have obtained it as parabola 9 kilonewton meter at the midspan. For the span BC, it is a 6 kilonewton meter, and this 6 kilonewton will be at the place where this 5 kilonewton load acts. Okay. So there will not be any simple beam moment in the span CD. Now we can draw the fixed final end moments. End moments for ABCD. So final end moments we have calculated in our last step. So these are the final end moments. MAB is minus 8.018. So for MAB and BA. So when you are taking the span AB, MAB is negative, so anti-clockwise pointing upwards. MBA is positive, clockwise pointing upwards. That means our bending moment diagram will be like this. So 8.108 and 1.784. When you are considering the span BC, MBC is minus 1.784, so it is anti-clockwise, upwards, pointing upwards. MCB is plus 20, so it is clockwise, again pointing upwards. So it will be like this, this is 20. When you are considering the span CD, at C, it is negative, so pointing upwards. We have a 20 kilonewton meter here. At D, no, you will not have any moment at D, because it is an overhang. This is an overhang. So we know this 8 kilonewton load is acting at the midpoint. So up to this you will have the moment. See, that means every point, this is why it is minus 20, because it is 8 into 2.5. 8 into 2.5, it is 20. If you take this point, if this distance is 1 meter, it will be 8 into 1. That means at every left side of this concentrated load, you will have moment. You will have the moment up to C. And the moment is linearly varying. Okay. So that is why at CD, your bending moment diagram will be like this. Now we will draw these diagrams in the original bending moment diagram. See, this I explained you for understanding. So at the A, it is minus 8.108, right? So approximately here. 8.108. At B, it is 1.784. See, everywhere it is kilonewton meter. At C, it is 20. And up to this point, we will have the load. After that, in this span, there will not be any bending moment. So our bending moment, fixed bending moment diagram is so our net bending moment diagram is see, which means here there is negative bending moment, positive bending moment, Negative bending moment. Everywhere it is negative. Okay, so from this point to this point we will have a hogging. Then from this to this we have a sagging. And from this to everywhere it is hogging. Sorry, yeah, hogging. So how will we draw the deflection diagram? Now we will draw the deflection diagram. So this is A, B, C and D. So our point of contrafluxes are, so A is fixed. We have point of contrafluxes here. Here there is a point of contrafluxion. That's all. Right? So our bending moment, sorry, our deflection diagram is comes like this. This is a hogging. Then it is a sagging, right? From here to here it is a sagging. Then again it is hogging. Hogging. Then it goes on like this. Okay. So this is our deflection diagram. And this is our bending moment diagram. So that is all for today. Thank you for listening. Next class we will proceed with the analysis of frames using Kanis method. Thank you for today. Thank you for listening.